Okay, g'day all. Welcome to another tute. Okay, so a little bit of an announcement first of all. Isaac 0.7 is nearly finished. So I've been making a AI language for a long time now, and I've decided to collect all my ideas together and make an interpreter for the language. So it's called Isaac, and the first version will be 0.7. That'll sort of be a proof of concept version, just to see if these ideas are any good. It's a brand new language. It's not based on anything else, and it's going to be used for sort of quick and hopefully relatively intelligent natural language processing. So processing English, basically. I'm hoping that things like, you hook it up to your Java program or your C# program or your C++ program and have your non-player characters speak natural English and understand sort of, typed English or English captured from a microphone or whatever. But keep an eye out on the Facebook and the website for updates on that. I think it's going to be pretty interesting. Anyway, that's enough advertising. Let's get on to the topic for today. So today we're going to start a little mini-series, much like the IEEE 754 mini-series that I did. This one is on what's called fixed point arithmetic. And, with modern computers, it's so easy for programmers to forget that there's other ways to deal with fractional numbers. So when you're dealing with fractional numbers nowadays on a modern computer, it's almost not even a question. You just use floating point. But the interesting thing is that there are actually other ways, such as this fixed point method. And sometimes you can do amazing things, like you get a lot of speed up using fixed point and that sort of thing. So we're looking at this topic. It's a very interesting topic, and it's all about a different way to perform arithmetic on numbers with fractional parts, a different way than floating point. So fixed point arithmetic's got advantages and disadvantages when compared to floating point, so let's just go through a few of those. First of all, it's got flexibility in precision, range and data size. That means that the programmer themselves chooses the precision, the range and the data size with fixed point arithmetic, whereas with floating point arithmetic, the precision, range and data size are already selected for us. They're set by the IEEE. Some operations are faster with fixed point, so that sort of particularly comes into play when you're dealing with SIMD. So when you choose the data size, for instance, if you choose bytes for your fixed point arithmetic, maybe you don't need very much range or precision, so you might choose bytes. And SSE, for instance, can do 16 or operations on 16 bytes at once. Whereas it can only do operations on 4 floats at once. So you're talking about a huge advantage there in terms of speed if you don't need the flexibility in range and precision. The other thing about fixed point arithmetic is that it's easier to do several operations, like your casting to and from integers are really easy, and also grabbing the fractional part. If you're dealing with floating point numbers, grabbing the fractional part can be a little tricky or a little time consuming, would say. But it's really easy with fixed point. Alright, so some of the negatives might be that some operations are slower in fixed point. I'm thinking particularly there of division and multiplication. They're not, they're not that slow, but they are slower in fixed point than floating point, depending on what you need to do. We'll go through that, I think, next tute. Precision is generally less in fixed point when compared to floating point. So usually in floating point, if you're dealing with, say, single precision floats, that's 32-bit floats, you'll get maybe 24 or something like that bits precision. And with fixed point, you might only get, 8 bits precision or 16 bits precision. It's up to the programmer. Also, range is generally less than floating point. So with floating point, the range is gigantic because they've got this exponent over the side. So floating point uses a scientific notation to represent numbers, and it's got a huge range because of that scientific notation. And fixed point doesn't use that scientific notation, so the range is considerably less. There's no inbuilt instructions for fixed point. That's not entirely true. What we'll see in a moment is that some of the instructions, at least, are perfectly normal integer instructions. The other thing to be careful of is that fixed point code can quickly become really, really confusing. But all code can become confusing if you're not careful. So fixed point arithmetic actually uses integer variables, and if you're not careful, you can pretty easily get confused. But I mean, why would you be programming if you're not careful? Yeah, we professional programmers here, we're not confused by that. That was a stupid point. Okay, so fixed point arithmetic, what are we talking about here? This is the crux of it. The idea is that we use integers, but we change their meaning. So if you think about it, any integer or any bit pattern inside the computer is really up to the programmer what it means. It's not set in stone. If you've got, say, 8 bits, they might be 8 different flag variables. It might be 8 different single bit variables, or it could be 2 4-bit variables. Any bit pattern in the computer's RAM or hard drive or anywhere at all, it's always up to the programmer what they mean. So what we do with fixed point arithmetic is we say that the integers involved in our fixed point calculation mean themselves multiplied or divided by some scaling factor. And we, the programmer, we choose that scaling factor. So that middle paragraph there is really what it's all about. We're just changing the way that we read the values of a bunch of integers. For instance, this is just a little base 10 example here, but when we get to code, we'll jump back to base 2, since computers love base 2, much as humans love base 10. But for instance, our scaling factor might be 1 over 10, or 1/10. And that would mean that if we've got an integer set to 6, what we'd be saying there is that it means 6 multiplied by 1 over 10. Or 6 over 10, in other words. Or 0.6 if you like. Likewise, with the same scaling factor, we might have an integer set to 28, and that would mean 2.8, or 28 multiplied by 1 over 10. So you see, all we're doing here is we're not changing the integers themselves. The integer's still going to have 28 in its bits. We're just changing what it means. We're saying that it means 28 multiplied by 1 over 10. Alright, so just a little bit about the scale before we get going. When we select the scale, what we're actually doing is setting the range and the precision of the arithmetic that we're about to perform. And with fixed point arithmetic, you tend to use the same scale factor for a whole bunch of variables. That's kind of why it's called fixed point arithmetic. We'll see in just a little while. But with computers, the scale is usually some power of 2, so it might be 1 over 2 to the power of 16, or 1 over 2 to the power of 24, or whatever. It just makes things easier, or certain operations easier. So the scale could, in theory, be any number at all. It doesn't have to be a power of 2. It doesn't have to be anywhere near the range of regular integers. You could make your scale 1 over 2 to the power of 560 billion if you want. It's completely up to you. But usually what you'll end up doing is making your scaling factor 1 over 2 to the power of, and then something in the range of an integer. So something in the range of 2 to the power of, 2 to the power of 0, all the way up to 2 to the power of 32. I'm going to be using a scaling factor of 1 over 2 to the power x, and what I'm going to do to set that scale is set this variable x at the top of my program. Yeah, I'll call it scale, but it's going to actually mean 1 over 2 to the power of x, even though I'll just say something like int scale equals 16 or whatever. We'll see that in action in just a minute. And what have we got here? If your application requires exact representations of this this is a hidden gem in fixed point arithmetic. We're not going to go through this today. We might look at it at the end of a future tute, but Usually, computers can't represent things like 1/3 or 1/7 exactly. The binary representation of 1 over 3 doesn't exist. So something like double precision or even the 80-bit floating point format, it can get very, very close to 1/3, but it can't exactly represent 1/3 without rounding. But with fixed point, you can actually represent exactly 1/3 or 1/7 if you like. We're not going to go through this. Like I said, we're going to be using powers of 2, but just for interest's sake, I want to mention that if your scaling factor is something like 1 over 3 times 7, or 1 over 21, then you can actually represent 1 over 3 and 1 over 7 exactly, and multiples of those values as well. With absolutely no rounding. So that's actually really, really interesting, but we're not going to look at it today. Okay, so fixed point in a nutshell. What we're saying, like I said before, we're saying that the variables involved in some arithmetic don't represent their normal integer values. Instead, they represent their values with some radix at a fixed position, some radix point at a fixed position. So if we just go back to floating point and its exponent, the IEEE 754 floating point standard, it's got these bits over the left hand side of the variables which is called the exponent, and that exponent actually changes the position of the radix point in the mantissa of the number. So the exponent can move that radix point up and down, and that's where the floating point system of representing numbers gets its name. The point is said to float, you know, it can move up and down. It's not in a fixed point, a fixed place I should say. But fixed point arithmetic, it is in a fixed place. We choose this this scaling factor, and by so doing we're selecting a particular point for our radix point to be at. And let's have a bit of a look at an example. So let's say we've got the bit pattern just here, this byte just here, and if you do a little conversion to base 10 from binary, you'll see that that means 118. Yeah, so it can obviously mean 118, that's the perfectly normal integer representation. But if we're using fixed point and we say that our scaling factor is 1 over 16, then what we're really doing is we're popping a radix point right there in the middle of those bits. Yeah, so our number would become 0111.0110, which is 7.375 in decimal. Or if you like, it's just 118 over 16. Yeah. Or maybe you've got your scaling factor set to 4. That would mean that that bit pattern there has a radix point right there at 2 from the right. I hope my mouse cursor is visible. Yeah, 2 from the right hand side. That would mean that the bit pattern 118 actually means 118 over 4, or 29.5 in other words. Likewise, you might set your scaling factor to 1 over 64, which would mean that your bit pattern 118 means 118 over 64, or about 1.84375. Yeah, that'd be it right there. So you can see by choosing different scaling factors, what you're doing is moving this radix about. But what you tend to do is choose one scaling factor for a bunch of operations. You don't tend to, you know, mix fixed point with some scaling factor with operations with fixed point of another scaling factor. Yeah, so you'll choose like 1 over 16 as your scaling factor, and you'll do that with all of your operations in some particular code block of fixed point arithmetic. Okay, let's just move on. So what we're going to do is a bit of coding. We're going to look at doubles to we're going to look at doubles to fixed point and vice versa. We're going to look at integers to fixed point and possibly vice versa. We'll look at grabbing the fractional part of fixed point, adding and subtracting, and we might also look at epsilon, which is the smallest unit of precision in some number format. Okay, so here I am in Visual Studio 2012. I've got 2013, but I don't use it that much. I will, I guess, eventually. I will change over. Who cares? Who cares? Okay, so what we want to do first of all, I'm going to be using C++. What we want to do first of all is just have a bit of a write out of a bunch of bits, just so that I can illustrate what we're doing here. So let's see, is that 31 or 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and... Okay, so that's going to be... Oh, that's an integer just there, written out in bits. That's just a hypothetical integer, but yeah, it might look something like that. So, first thing that we want to do is set a scaling factor. So, for me, I think it's easiest to set a const int at the start. I like to call it scale, and I like to set it to, say, 16 or whatever. But what that means is that the scale is 1 over 2 to the power of 16. Yeah, so the actual scale I'll be using for my fixed point arithmetic will be 1 over 2 to the power of whatever this variable here is. And you'll see how that comes into play in a moment, because a lot of the operations, the conversion operations, involve shifting. So that's how that 1 over 2 to the power of 16 will come into play. But that means that my radix point is right there. Yeah. So there's 16 bits to the left and 16 bits to the right of my radix. Or if I wanted, I could do this. Now I could put my radix point right there, and that would be that, a scale of 8. It's completely up to you. Or you could make it a scale of 24 if you want, put your radix point there. It's completely up to the programmer, depending on what sort of precision and range they need. Anyway, so the first problem that you might come into is how to convert a double to fixed point. So I'm going to call my fixed point variable f, and you'll notice that I'm just going to use an integer here, and I'm going to make a function double to fixed point, or double to fixed I'll call it, and I might say 5.7. Okay, so I'm going to make a function that converts a double to fixed point. Now this is largely for illustrative purposes. When you're in the middle of a fixed point arithmetic problem, you'll often not want to convert to and from doubles. You kind of convert all of your parameters from doubles at the start, and then when you're in the middle of a tight loop using fixed point arithmetic, you don't want to be doing this conversion. You'll lose all of the speed benefits that you'd otherwise gain from fixed point. But for illustration, this is very, very useful. And you'll often have to convert your variables from doubles to fixed point anyway, so it's a handy function. I'm not actually going to make a function. I'm just going to make a defined. Alrighty, so what do we want to do here? X multiplied by, it's going to be 1 that way, scale. And that's a double. And the whole thing is a double, and surround it with braces. Okay, I might change my scale back to 16. Okay, so that's the define right there. Well, that's the function right there. You could write it as a function. I've just used a macro, but it's up to you. I don't think the macro will be a lot faster either with an optimizing compiler, but I just like to do it this way. If you multiply the double 5.7 by 2 to the power of 16, you'll get your fixed point value. Yeah. It's not really that good unless we can check what the value looks like. So what we might want to do is convert it back to a double so that we can see out the value. So if you see out just a fixed point number, it's not going to look like what you want. It's just going to look like some gigantic integer. But to convert back again, what have we got to do? We've got to do the opposite operation. So x divided by 1 that way scale. Yeah, so that should just about give us the... And these are both doubles as well. And surround everything in brackets. If you're working with macros, if you're working with defines, you should always put brackets around everything at the end. Brackets around your whole expression at the end. Just to make sure that the compiler doesn't get confused when you're using your macro in the middle of some other expression. Anyway, let's have a bit of a look at what this 5.7 has become. This is going to be interesting. I don't know if this is going to work actually. It's fixed to double and f handle. Okay, let's have a look. So it should be about 5.7. And there you go, it is exactly 5.7. Actually, it won't exactly be 5.7. This is just the precision of cout. But what's cool about that is that f just there is an integer. Yeah, so we've managed to save 5.7 to an integer variable using fixed point. How weird is that? It's about to get weirder. But let's also have a look at the actual precision that we're getting here, because I know that 5.7 can't be represented, with fixed point like we're doing here. 1/7 is just impossible for binary to represent unless you're using fixed point with some multiple of a power of 7 or whatever, like we said in the slides. Anyway, let's just have a bit of a look at the precision. I'll change the precision to 20 and see what we get. Yeah, there you go. So it's not actually 5.7, it's 5.6999, blah, 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 blah. It's pretty close to 5.7 though. Let's have a look. I think also that the doubles won't actually... A double won't actually represent 5.7 either, so let's have a bit of a look at the precision there. This should be a lot higher. Yeah, there you go. So that lower number just there is the double, 64-bit double representing 5.7, and you can see that it's much more accurate. It's really, really close to 5.7, and the fixed point version up here is a little bit wayward, but it's pretty good, really. Let's see what happens if we change our scale to 8. So changing the scale to 8 is going to move the radix point from there, from the middle of our integer, over to here. And it's going to mean that we don't have anywhere near the kind of precision that we had to the right of the whole number. Let's have a look. Yeah, there you go. So 5.6992185. So it's still pretty close to 5.7. Yeah, and what we've done there by moving that scaling factor, or the radix point there, to the right hand side of the number, is we've really opened up the range of our fixed point precision here. So you don't really get that kind of option when you're dealing with floating point. The range and all of that, it's already set for you. But with fixed point, you get to choose. So we could put it here if you like. Yeah, we'll put it there. So if we put our radix point right there, that's I think 24. Yeah, 24. So with a radix, with a scale of 2 to the power of 24, or 1 over 2 to the power of 24, we've got a very small range. So we've only got 8 bits at the top, and that's going to be a signed byte too. So it'll be what, 127 to negative 128. Yeah, that'll be our range. But we'll have a lot of precision to the right of the radix. So let's have a look how close we can get with that to representing the 5.7. There you go, pretty close really. So 5.6, a bunch of 9s, 880790, yeah, whatever. Pretty close. Yeah, so that's how you can convert to and from doubles. If you want to convert an integer to fixed point, it's pretty easy as well. I wonder what I was just typing. It looked like index. Why would I type index? Int to fixed. Converting integers to fixed point is really easy as well. You actually just have to shift them. Yeah, like that. Yeah, so if this was an integer, say something like 6, and you go int to fixed, we should end up with 6. Yeah, there you go. There you go, 6. I might just get rid of those lines now. Okay, so we've got little functions now to convert double to fixed, fixed to double, int to fixed. Maybe we want a fixed to int. That's pretty easy as well. It's the opposite function to what we just did with int to fixed. No, it's not that opposite. Settle down. They're trying to swap the operands around as well. That's not going to work. There you go. So fixed to int is just a matter of shifting right by whatever the scale factor is, 2 to the power of 24 in our case. I might actually change that back to 16. Okay, so some operations to add two fixed point numbers is pretty easy. It's actually just perfectly normal integer arithmetic. So if we've got two fixed point numbers, I'll call them f1, and I might say double to fixed, and we'll say like 5.6, and int f2 equals double to fixed 7.9. So to add these two together and maybe store the answer in f1, it's just an integer addition. F2. Yeah, there you go. So that's one of the big benefits of fixed point arithmetic, is that addition is super easy. We can see out the answer just to make sure that we're in the right ballpark. Well, yeah, we could see out f1. What's that going to have? What's going to happen if I see out f1? It's not going to be good. There you go. 884,000, bro. What I actually meant to do then was convert it to a double to see out. Yeah. Yeah, so the actual value of the fixed point number is not particularly relevant. What you want to do is convert it to a double if you want to print it out. But, like I said, when you're in the middle of a loop, you don't want to be converting to and from these things. Oh, that's the wrong way. It's fixed to double. Yeah, that's it. Okay, that's better. That's better. 13.499. Let's have a bit of a look in our calculator. 7.9. Okay, so the actual answer is 13.5 according to my Casio scientific calculator FX100AU. Okay, and the calculator rarely lies, but what we can do is just reduce this precision a little bit and hit play again. Okay, so it's about 13.5 according to cout, when cout's precision is about 5. So that's pretty good. Integer addition will give us fixed point addition. Subtraction is equally as easy. So if we want to subtract two fixed point numbers, we just use integer subtraction. Subtraction. Okay, so this should give us, I don't know, negative 2 point something. Negative 2.3. There you go. So 5.6 minus 7.9 is negative 2.3. But we figured that out using integer arithmetic. Is that beautiful or what? Okay, so if I just hit stop, put my radix point back there since we're using a scale of 1 over 16. Okay, so I want to talk about epsilon. Epsilon is the smallest possible precision, the smallest possible increment or decrement that you can perform on a fractional, system of representing numbers. And for fixed point arithmetic, epsilon is just a 1. Yeah, if you just put a 1 in there and then you convert that to a double, I just can't even type epsilon for some reason. There you go. So that's the smallest possible number that we can represent with our fixed point system when our scale is 1 over 2 to the power of 16. 1.5259 by 10 to the negative 5. If I hit stop and we change that to, let's put it right there. Let's put our decimal point right there. So to put my decimal point right there, all I've got to do is change my scale to 2. Okay, so this is going to give us an epsilon that's really quite large. I think it should be like a quarter or something like that. Yeah, there you go. So epsilon is a quarter if your scaling factor is 2 to the power of 2. Good stuff. So if you increment one of these variables, say I increment this, f1 just here, if I just say something like f1 plus plus, just like that, what I've really done is added epsilon to 5.6. Yeah, or decrement is just like that. That's subtracting epsilon. Okay, so I think there was one other thing that I wanted to go through. Let's have a bit of a look. Oh yeah. So extracting the integer and fractional parts of fixed point numbers is the final thing that we want to go through. So first of all, I like to define a const int called the fraction mask. You can call it whatever you want, but okay, if I put my radix back in the middle and have a bit of a description about what's going on here. To extract the fractional part of a fixed point number, what we want to do is make the top part, or everything to the left of the radix point, we want to turn that into a 0. And everything to the right of the radix point, what's he doing over here? Everything to the right of the radix point, we want it to remain. So what we really want to do is Boolean AND with that value. Yeah, we want to perform a Boolean or a bitwise AND between our fixed point number and mask out whatever's to the left of the radix point. So the way that I like to do that is define this const int called fraction mask and define it with respect to this scale value here. So equals ox ff and that way by 32 minus scale. Yeah, so that'll be our fraction mask right there. So if I change this scale value, then there'll be ones over here or whatever, but there'll always be ones wherever the radix point is. So that's my fraction mask. With 16, it's going to look like we had before. It's going to look like that. And then to actually take the fractional part of a fixed point number, all you've got to do is AND. So I might just define another, I'll call it fractional part, x and fraction mask. That's how you take the fractional part. So let's just have a bit of a go with this f1 just here. Let's see if we can take the fractional part and see out it to the screen. So that's almost what we want just there. If I see out, if I see out the fractional part of f1, I'm not actually going to get 0.6. What I'm going to get is the integer part, so I'm going to get this number just here written out as an integer, without the radix point. So I want to actually convert that to a double first. Let's have a look. So it should give us 0.6. Well, there you go, 0.59999. So it's pretty close. It's trying to do. It's trying to do 0.6. Can't quite get there because of the 3 is a multiple of 6, so it's having a bit of trouble. But if we change the precision, maybe we move the decimal point up there by changing the scaling factor to 1 over 2 to the power of 24. Let's see if we can get closer to 0.6 now. There you go. So now it's really close to 0.6. That fractional part there of 5.6. Let's type in another number and see how it goes. So let's type in like 23 point that without the y in it. Okay, so that's a pretty wayward number. That's all over the shop. Let's see how close we get. Okay, so the fractional part it's saying is 0.67873. 6787. It's pretty close. Yeah, it's really close. Let's have a look. We'll get rid of this precision, change it back up to 10 and see how we go. Okay, 6787259. 272. Okay, it's really close. Yeah, it's really close. Okay, so it's not exactly right, but who cares? Okay, so that's how to take the fractional part of a fixed point number. The other thing that you might want to do is just take the integer part of a fixed point number. I want to say also that that's a single integer AND instruction right there. It's really, really fast. And if you were doing that, what we just did, if you were doing that with doubles, the usual method to accomplish that is to convert the variable to an integer, then convert it back to a double, then perform a subtraction of that integer part, leaving just the fractional part left. And that's pretty quick and all, but this is much, much faster. This is like 4 or 8 times faster than that operation. It's really fast. So this is one of the big benefits to using fixed point, if you've got to take the fractional part of a lot of numbers. Okay, so the other thing that we might want to do is just take the whole part. So I'll call this the whole mask, and I might just define it in terms of the fraction mask. So if we get the value -1 and we XOR it with whatever the fraction mask is, then we'll get a whole mask. So if you XOR some bit pattern with all ones, what you end up doing is flipping all of the bits. So what we'll have now is, instead of our, let me just change this back to 16. Instead of our mask being like that, which was good for extracting the fractional part. Why is there one missing on the end? Which is good for why is there? Oh, it's here. Which is good for extracting the fractional part. Now our mask is going to be all ones over this side, and over this side, on the fractional side, it's going to be all zeros. Yeah, so that's what the whole mask looks like. Anyway, let's see how she goes. So instead of fractional part, we want to define one more function. Define whole part x, and it's x and whole. What did I call it? Whole mask. I should probably make all of those uppercase instead of being such a sook and making camel case or some random case. No. Okay, so this should give us 23, I think. Let's have a look. We're extracting the whole part of this fixed point number, but it's, 23. There you go. So it's still actually a fixed point variable at that point. Yeah, we haven't converted it to an integer by shifting it back again. And when you convert to an integer, you actually discard all of this stuff, all of the fractional part. But let's have a look, just for interest's sake, at what 23.6787 whatever actually is as an int. Well, there you go, 1,507,328. Yeah, so that's the number it's actually storing. Yes, okay, so that's just a bit of basic arithmetic and a little introduction to fixed point arithmetic. I think next shoot we should look at multiplication and division, because things get a little bit scary right there. But, you know, there's tricks to do that as well. So I hope that was really interesting. As far as I know, there's not a lot. There's not a lot out there on this topic, but it's a really good topic, and hopefully you find it useful and interesting. Anyway, I'll see you next shoot. Thanks for watching all.